Hello, welcome to this crash course on distributed systems. Most people meet this field as a vocabulary list: quorums, vector clocks, write-ahead logs, raft, consistent hashing, and so on. Every item is individually explainable, and the list as a whole never quite adds up, because the mechanism doesn't really make sense until you know which problem forced it into existence, and a list doesn't tell you that. So we're going to build the problems first, in order, and let the mechanisms arrive as answers. We're going to learn distributed systems through what I'll call the Assumption Relaxation and Constraint Introduction Framework. Here's the idea. We start from an idealized baseline, a single, deterministic machine operating under perfect conditions, with infinite computational resources, zero latency, and complete immunity to failure. Under that baseline, a distributed system collapses into ordinary sequential computing, and there is nothing distinctive to say about it. That's the point. It gives us a floor. Then, from that ideal foundation, we relax the underlying assumptions one at a time. Each relaxation introduces exactly one new real-world constraint. We examine the problems that constraint creates, and we progressively develop the solutions, the mechanisms, and the trade-offs that the distributed systems literature has produced in response. Because we relax assumptions one at a time, rather than all at once, the interactions between successive constraints and the core desirable system properties, consistency, availability, latency, and fault tolerance, become traceable rather than tangled. If this reminds you of the fallacies of distributed computing, the well-known observation that engineers routinely design as though the network were reliable, latency was zero, and bandwidth infinite, then you're seeing the family resemblance correctly. But there's a difference. Where the fallacies name a set of independent false beliefs, the assumptions we develop here are deliberately ordered, so that each relaxation builds on the last, and they extend beyond networking to cover storage economics, data volume, and throughput as well. The objective is to weave the standard concepts of distributed systems into a single logical interconnected narrative rather than presenting them as a catalog of loosely related mechanisms. We want breadth of coverage and we want conceptual coherence. The chapter-by-chapter ordering is itself a pedagogical choice. Each mechanism is introduced only once the constraint that necessitates it has been established, so that it arrives an answer to a specific problem rather than as an isolated fact. If you're new to this material, treat what follows as a conceptual roadmap, a structured way to navigate distributed systems by seeing how practical realities reshape the idealized model chapter by chapter. If you're an experienced practitioner, treat it as a refresher through a different lens, one that connects mechanisms you already know through a single unifying framework of assumption, relaxation, and constraint introduction. And in either case, I'd encourage you to consult the works referenced at the end of the course for a deeper, implementation-level treatment of any individual topic. Use this material primarily as a conceptual scaffold for system design thinking rather than as an implementation guide. One practical note before we begin: this course uses a single visual language, and it's used identically throughout. The same shape always means the same thing, the same color always means the same thing, and nothing on any frame is decorative. Most of it will read at a glance, so I won't walk you through the legend. But do pay attention to the small meter in the corner of every frame, which shows all 7 assumptions and their current status: relaxed, being relaxed right now, or still standing. Read it as the frame's fine print. Whatever the visual shows you is true only under the stack printed above it. And that discipline is worth making precise right now. So before we start relaxing anything, let's do exactly that. We're going to track the state of our model using 2 ordered collections. The first is a stack of remaining assumptions, which we'll call A. The second is a list of accumulated real-world constraints, which we'll call C. The assumption collection follows the semantics of a standard last-in, first-out stack. A constraint collection is append-only. At each stage, exactly one assumption is popped from A, and the corresponding constraint is appended to C. That gives us a very useful property. The system described in any given chapter operates under all the assumptions that have not yet been popped and all the constraints introduced so far. Every conclusion we draw in a chapter is implicitly qualified by the current contents of A and C, and it is subject to revision once further assumptions are relaxed. This is exactly why several of our results will be explicitly revisited in later chapters. A conclusion that holds given synchronized global clock, for instance, may no longer hold once clock synchronization is relaxed. We'll make that point explicit in chapters 4 through 6. And that is the rule the meter is there to enforce. A conclusion drawn while an assumption is still in force is not a conclusion you may carry forward past the chapter that removes it. Initially, no constraints have been introduced, and all 7 idealizing assumptions are in force. The stack is full, and the constraint list is empty. Let me state the 7 assumptions. A1. The process assumptions. A single, infinitely powerful machine with unlimited processing cores is available. All processes represent instantaneous state transitions, and no process ever fails. A2. The storage assumptions. All memory and disk operations complete in infinitesimal time, independent of data size or memory footprint. Both memory and disk are non-volatile, and all computational resources incur equal marginal cost with respect to both time and money. A3. The data volume assumptions. The total data volume never exceeds the storage capacity of a single machine. A4. The throughput assumptions. The system's read and write throughput never exceeds the computational capacity of a single machine. A5. The network assumptions. Network latency is infinitesimally small, bandwidth is infinite, and message transmission latency is entirely independent of the physical distance between nodes. A6. The clock assumptions. All machines share a single universal notion of time, synchronized to one perfectly accurate global clock. And A7. The failure assumptions. No failures of any kind occur, no power outages, no node crashes, no network partitions. Note carefully that A7 concerns hardware, operating system, and network failure. The software level failure of an individual process is a separate matter, and we'll address it in the very first chapter. Each of these 7 assumptions is relaxed in turn over the 7 chapters that follow, in order, from A1 through A7. Each relaxation introduces exactly one corresponding constraint, C1 through C7, and each chapter examines the complexities and design trade-offs that the newly introduced constraint reveals. Think of it as a map you can hold in your head. 7 rows. On each row, the comfort we give up, the reality we accept in exchange, and mechanisms that only become necessary at that row. Nothing in a lower row could have been motivated in a higher one. With that background, let's dive in.